Hello, and thank you for viewing this webinar. The purpose of the webinar today is to provide information related to the Receiving Pervious Area, or RPA, fact sheet. My name is Andrew Earls, and I am one of the co-authors of Chapter 4 of Volume 3. I am a senior stormwater engineer and hydrologist at Wright Water Engineers. This webinar is part of an on-demand webinar series related to updates to Chapter 4 of Volume 3. The Mile High Flood District is also developing webinars related to the spreadsheet tools that are used to implement the criteria in Chapter 4. This webinar focuses on the RPA fact sheet, which is important for achieving runoff reduction objectives of Step 1 of the 4-step process. Future webinars will cover additional fact sheets and specific aspects of the front section of Chapter 4. Finally, we are planning to hold periodic office hours to allow users to pose questions related to specific aspects of the chapter and fact sheets in an informal online setting. RPAs is a new fact sheet that we created from the previous grass buffer and grass swale fact sheets. RPAs include buffers and swales, but are also more broadly defined in the current fact sheet. RPAs are defined as any pervious area that receives runoff from an impervious area, and these RPAs are important for disconnection of impervious areas. There are many pervious areas in the built environment, and planning how to strategically use these areas to slow down and allow opportunities for infiltration of runoff is important in stormwater design. Examples of RPAs include traditional grass buffers and swales like the ones I'm showing on this slide. The key to RPAs working effectively is dense turf-forming grasses that slow down runoff and promote infiltration. RPAs can also include pervious areas that may not strictly meet the old buffer criteria in terms of width or other parameters, but that still provide significant runoff reduction benefits. And the images that I'm showing you on this slide on the left is a site in Westminster where you have a receiving pervious area that allows for shallow ponding and infiltration of runoff from the surrounding impervious areas. The photograph on the right is an example of a receiving pervious area that downspouts are draining to from a roof area. RPAs are very well suited for downspout disconnection, among other things. The photos that I'm showing you on this slide on the left-hand side is from the Taxi development, where you have an extensive RPA connecting multiple downspouts, providing runoff reduction. The photo on the right is actually from North Boulder, and although those are smaller RPAs, they still are providing opportunities for infiltration. The water from the downspout is providing some water to help support the plants, and that is in turn helping to reduce runoff and reduce the amount of irrigation that's required. So these are both really good examples of applications of RPAs. To understand RPAs, it's important to understand the 4-cover land use model that's in the Mile High Flood District's manual. This model breaks down any land use into 4 different types of surfaces. First, we have the UIA. That is what we refer to as unconnected impervious area. That is impervious area that drains over a receiving pervious area, or RPA. We also have DCIA. That is directly connected impervious area. That is impervious area that drains straight to the stormwater collection system without passing over a receiving pervious area. Of course, we have RPA, which is the subject of this webinar, and that is pervious area receiving runoff from the UIA. And we also have separate pervious area. That is pervious area that does not receive runoff from impervious areas. And although it may not produce a lot of runoff from an SPA, it's really in some ways can be a lost opportunity for potential treatment if that SPA could be lowered and instead serve as an RPA. Some of the benefits of RPAs relative to more conventional drainage approaches include volume reduction, a reduction in delay in peak flows, a reduction in the frequency of runoff to the drainage system, and shallow groundwater recharge, among other benefits. RPAs act as runoff reduction stormwater control measures that slow down runoff through vegetative resistance and allow for infiltration. For buffer type RPAs to work properly, sheet flow conditions must be provided. If flows concentrate, only a portion of the vegetated surface will be effectively being used for infiltration. Therefore, you must spread the flow out using things like level spreaders or slotted curb. Even for swales that convey concentrated flow, you can consider using banks as buffers to allow runoff from upgradient areas to enter the swale as sheet flow. Vegetation is important for proper functioning of RPAs. Dense turf grass is desirable. We recommend avoiding bunch grasses because those can leave a lot of bare ground between the plants that can create preferential flow paths through the buffer. Also, irrigation is going to be needed even if you're using natives, at least for the establishment period and potentially during future periods of extended drought. The vertical drop is another critical component of an RPA, and that's illustrated by the photographs on the right-hand side. The idea is to provide a 3-inch drop at the edge of the concrete to allow some room for the vegetation to grow up between maintenance cycles without allowing the vegetation to obstruct flow onto the buffer, like the photo at the bottom labeled 2018 is showing. Sometimes we're asked if rock-lined swales or buffers can qualify as RPAs. While rock-lined swales or buffers could be effective at reducing the volume, rate, and frequency of runoff, they generally would not have the same performance as vegetated buffers or swales that provide filtration and straining from vegetation, enhanced infiltration due to roots, water and pollutant uptake by plants, and microbial activity in the plant's root zones. So, non-vegetated RPAs, including permeable pavement systems, can provide runoff reduction benefits, but they generally do not have the same level of benefits or treatment as vegetated RPAs. Of course, healthy topsoil is a precursor for healthy vegetation. The Mile High Flood District's topsoil management guidance goes hand in hand with many of the SCMs in Chapter 4, Volume 3, including the RPA fact sheet. Without healthy topsoil, it's unlikely that an RPA will achieve the density of vegetation needed for effective treatment. We also include expanded guidance on level spreaders in the front section and guidance on protecting RPAs from compaction during construction. The fact sheet includes general guidance on RPAs as well as specific design procedures and criteria for buffers and swales. We tried to be somewhat less prescriptive with criteria, for example, the minimum buffer widths, than in previous versions of the fact sheet, to encourage more widespread implementation of these practices. In many places in the urban environment, pervious areas can be strategically placed to serve a water quality function. A good exercise in site plan development is to carefully evaluate all of the pervious areas on a site so that you can avoid missed opportunities where separate pervious areas that do not receive runoff from impervious area could instead serve as receiving pervious areas. Now let's run through the design procedures. We have design criteria and procedures that apply to all RPAs and specific procedures for buffers and swales. Let's start with the general procedures and criteria applicable to all of the RPAs. We always start by applying the four-cover land use model to a site to identify areas of UIA and RPA, and also adjusting plans to try to maximize the amount of RPA. Once potential RPAs are identified, they must be protected from traffic and other types of compaction. It's much better to avoid compacting RPAs than it is to try to decompact them after they've already been compacted. The next step is to characterize the on-site topsoil for suitability for the RPA. You need to provide at least 6 inches of good quality topsoil. In some cases, this may require importing topsoil or amending the on-site soils in accordance with MHFD's topsoil guidance. As previously noted, selecting appropriate vegetation is critical. Use a turf grass to achieve a uniform density of 80% or more, and provide irrigation, even for natives, at least during the establishment period, and potentially for future droughts. In addition to the general procedures and criteria, the following procedures and criteria apply for grass buffers. To design and quantify the performance of buffers, we start by defining the UIA and RPA pair. The ratio of the unconnected impervious area to the receiving pervious area is a critical design parameter. Better treatment is provided at lower ratios, for example, 2-to-1 or lower. We allow this ratio to be as high as 10-to-1, but at a ratio this high will require more maintenance and it will not be as effective for runoff reduction as a lower ratio. The interface width is another key design parameter. The interface should be designed so that there is sheet flow from the UIA onto the RPA across the interface. In the updated fact sheet, we no longer specify a minimum buffer length. However, longer buffers will generally provide better treatment than shorter buffers. Of course, if you have a very long buffer, flow may begin to concentrate, and intermediate level spreaders may be needed if this is the case. We've integrated some guidance from Dr. Bill Hunt at NC State University on this topic. He is somebody that has extensively studied level spreaders and buffers. The buffer slopes should be a minimum of 2% to achieve positive drainage, but no steeper than 3-to-1 horizontal to vertical. The maximum slope specified is related to the potential for erosion and also the maintainability of the buffer. The 3-inch drop from the UIA to the RPA is a critical design component, as we just discussed, and this is to allow for some growth of vegetation between maintenance cycles without impeding flow onto the buffer. The final step in the process for buffers is to calculate runoff from the UIA-RPA pair and to calculate runoff reduction. This can be done using the Mile High Flood District's SCM design workbook. This slide presents the additional design procedures and criteria for grass swales. The first step in the procedure is to delineate and characterize the areas tributary to the swale. To design swale inflows, consider sheet flow and concentrated inflow. You can use the banks of swales as buffers to provide filtration of inflows that can be enter the swale from upgradient areas as sheet flow. Of course, many swales also have concentrated inflows, and if this is the case, provide a sediment pad or a forebay, depending on the magnitude of the inflow, the concentrated inflow to the swale. The next step in the process is to define the swale cross-section. Swales should generally have a trapezoidal cross-section and should not be steeper than 4-to-1 horizontal to vertical on the side slopes, and preferably flatter. We only count the bottom width when we're determining the benefits of the RPA and runoff reduction. Maximizing the bottom width will increase the wetted perimeter, and that will lead to more runoff reduction. So consider that when you are designing swales for runoff reduction. Swale slopes should be at least 2% for positive drainage. Swales may be sloped more mildly, but if that's the case, you may need to use an underdrain. In addition, you need to watch out for very steep slopes for swales, because those can create erosive velocities. If you have steeper swales, you may want to use check dams. Those can be used as grade control, and they reduce the velocities and also promote and enhance infiltration. Based on watershed and geometric parameters, we then calculate runoff. Runoff reduction is calculated based on infiltration through the swale bottom. We also want to calculate peak flow rates for design events from the water quality event all the way through the 100-year event. Use the 2-year event to assess swale stability, in other words, the allowable velocities, and use the WQE to assess runoff reduction. Always check the 100-year event to be sure that you're not causing any unintended flooding. The design velocity ideally should be less than or equal to 1 foot per second for the water quality peak flow rate for water quality swales. Higher velocities, up to 3 to 5 feet per second depending on the soils, are acceptable in the 2-year event, and that's a part of the swale stability check. You should use the NRCS vegetal retardance curves to determine Manning's N for the hydraulic analysis. The design depth should not be any greater than 1 foot if you're using the swale for MS4 runoff reduction purposes, and that would apply to the water quality event. Of course, if the swale also will convey larger flood events like the 2-year event or the 10-year event or even the 100-year event, then the depths can be deeper in those larger events. Finally, it's important to know what the swale will flow into, whether this is another open channel or an inlet. The outflow must be evaluated to determine if the outlet has capacity for the swale flows and if the outlet hydraulics have the potential to cause any sort of a backwater effect in the swale. In addition to good design, careful management of construction is critical for a successful RPA. You must be sure that the as-constructed conditions will result in sheet flow. If they don't result in sheet flow, the RPA is not going to work, and typically, especially for larger drainage areas, level spreaders will be needed to achieve this. One of the things that I like to say is that if it doesn't get wet, it's not an RPA. So think very carefully about how flow is spread out across RPAs, because if an RPA doesn't get wet, the part of the RPA that doesn't get wet is not contributing anything to runoff reduction. Also, avoiding compaction is one of the most important construction considerations. Compaction can ruin an RPA before it even goes into service. And it's really preferable to avoid compaction versus trying to decompact soils that have already been compacted by construction equipment. Compaction is really the enemy of RPAs because it reduces the pore space in the soil that's critical for infiltration. RPAs rely on the pore spaces within the soil to provide pathways to allow runoff to infiltrate into deeper soil layers. The pores also allow for air to get into the subsurface, which is important for the health of vegetation. When soils are compacted, the infiltration capacity of the soil can be reduced by an order of magnitude or more, and the plant roots can have a difficult time establishing a dense network of roots when you have heavily compacted soils, like I'm showing on the right-hand side of this slide. Maintaining high infiltration rates for RPAs is critical because they must provide infiltration of runoff from adjacent unconnected impervious areas in addition to infiltrating the rainfall that falls directly on the RPA surface. Additional construction considerations include staggering of sod tiles when you're installing sod for an RPA, maintaining erosion and sediment control measures, providing irrigation, as we've discussed previously, managing weeds, and posting signs like the one shown on this slide to restrict access while vegetation is becoming established. While RPAs are low-maintenance stormwater control measures, they are not no-maintenance stormwater control measures. More and more frequent maintenance should be expected when you're using higher ratios of UIA to RPA because the RPA is basically acting like a filter. Mildly sloped swales, typically less than about 1 or 2%, may need underdrains to avoid soggy bottoms. Steeper slope swales also may require some special treatments, including check dams, to avoid creating erosive velocities and to promote infiltration. You should use healthy weed-free topsoil, and this will help to reduce your maintenance requirements during establishment and also over the long term. We recommend adaptively managing irrigation following establishment. While irrigation is critical for establishment and may be needed during drought periods, you also want to avoid over-irrigating RPAs because they work by having some residual capacity to absorb moisture in the soil. It's important to think about maintenance when you're designing for mowing. Milder slopes will make mowing safer and also will provide greater water quality benefits. You should not store snow on RPAs. When snow is scraped off of an impervious surface, it has a lot of fine particulates with it, and as the snow melts, those fine particulates can clog an RPA. RPAs are not the right place for snow storage. We also, of course, have to protect the RPA from traffic, and using fencing or signs are a couple of different ways to do that. That brings us to the end of this webinar. You can access Chapter 4, Volume 3 at the link provided on this slide, including the RPA fact sheet. If you have any questions, we'll be holding office hours in the near future, so please monitor the Mile High Flood District's website for this and other upcoming training opportunities. Thank you for attending this webinar.